Hello everyone, this is my first lecture that I've ever recorded, so bear with me, you can let me know what worked, what didn't work, etc. Okay, so this is covering chapter 4. Please read the chapter before this lecture, or immediately following, so it's fresh in your brain to put the pieces together. So this is on chapter 4, we're covering Newton's first law. Now Newton's first law is basically stuff wants to keep doing what it's doing, unless something else acts on it, changes it. The sciencey way of saying that is every object continues in a state of rest or of motion in a straight line at a constant speed unless it is compelled to change that state by forces exerted upon it. But that's just stuff wants to keep doing what it's doing. So the idea is ball is moving, it will keep moving in a straight line at that same speed. So the ball is moving 5 miles an hour, that ball will keep going 5 miles an hour in a straight line until Jesus comes back, unless another force acts on it. The idea is that rock or that ball is sitting on your kitchen table. It will keep sitting on that kitchen table unless someone kicks it or it bumps it, acts on it, and then it will move. Here's a better example. So the Greeks got the part about motion. The ancient Greeks, they looked at a rock sitting in the middle of the field, and they're like, if the rock is still sitting, the rock just is sitting in that field. If that rock, you're watching a rock in the middle of a field, and that rock suddenly jumps up and moves, you're going to decide something happened to that rock. Someone shot it from far away. There's a creepy little alien creature living on the inside of it. Like something happened to that rock to make it move. Rocks don't just get up and move or just start rolling. Like that's not what we expect, because we innately understand the half of Newton's first law. We innately understand things that are just sitting there, things that are just resting, aren't going to suddenly start moving unless a force was acted on it, unless someone shot it with a space laser. Sweetie, don't eat crackers, it makes too much noise. Sorry. Unless something happens to it, it's just going to sit there. The Greeks got that. We got that. Babies get that. We figure it out. The part that the Greeks missed, and that babies missed, that we probably missed as children, is the idea that something will also just keep on moving unless a force is acted upon it. The reason the Greeks didn't get this is because friction and gravity. And almost everything that we see or interact with in our day-to-day lives has friction and gravity. Now, I say everything we interact with in our day-to-day life. You know that if you kick that rock or kick that ball, it will stop rolling eventually, even if you're near a super flat field. You know that if you throw that baseball as hard as you can, it will eventually hit the ground. So in the baseball, it was gravity that pulled it down eventually. With kicking your soccer ball, it's the friction of the grass and everything. And so because of that, Greeks decided, well, things like to be at rest. But that's not actually true. It's not that things like to be at rest. It's that Newton's first law is that things will keep on doing what they're doing unless a force is acted upon it. In this case, it's the force of friction. The friction that is eating up the speed of that soccer ball. The same way when I throw a ball straight up in the air, gravity is eating up the energy or that I threw up that ball with, and then it comes down. Let's see. Interesting note though, the Greeks knew that things kept moving in the heavens because they looked up, they could see the planets just kept on moving, and they didn't see anyone kicking the planets or jet engines firing off in the back of the planets to keep them going. They saw the planets just kept on going. So they had a hint. The Greeks had a hint that things do keep on going, keep on moving, unless a force is acted upon them. What they incorrectly assumed, though, was that, okay, there's a second set of rules for things in the heavens, and there's a different set of rules on things on the earth. They're kind of right, but what was much more right is that there's actually one set of rules. We just have different inputs. We have different things going on earth. That's friction. Okay, so, let's see. Sorry, I'm looking at my notes here. And it's cool that there aren't multiple rule sets. There's like one rule set that changes a little bit with the whatever inputs you put in. There's one box. If you put flour in it, cookies come out. Or if you put flour and sugar in it, cookies come out. If you put flour in it, bread comes out. But there's one box. It's like what you put in, what you get out of it. Sorry, that was not the best analogy in the world. Friction and gravity. So, example with the soccer, one of the hints that we have that it's friction is if you're familiar with ice hockey, can you imagine trying to play ice hockey on a carpet? How far is that puck gonna go when you hit it? Now, so we can see on a carpet, imagine trying to play ice hockey on gravel. Imagine rougher and rougher surfaces you're trying to play that hockey on. And now we imagine the ice rink, and even ice has a tiny, tiny bit of friction. So now we imagine how far would that puck go if you had frictionless surface to actually play your hockey on, and you see that it'll go farther and farther and farther. When you finally get to that utterly frictionless infinite ice rink, it will just go on forever and ever and ever. When you hit it once, it will go sailing on until Jesus comes back, which is very similar to what Voyager 2, that satellite that we sent out past Pluto, it's going and going. It has no new engines firing off in it. It's not burning any more fuel. It's just going because the last push it had just goes and goes through pretty much frictionless space, and it will keep on going unless it smashes into something or until the universe is ended. Okay, let's see, one more note. Sorry, I'm good at going over notes. Okay, so this is important. So the Greeks said to stay in motion, something has to keep getting more forces act on it. You need to keep pumping energy into the system. Example, when you're playing soccer and you're getting that soccer ball across the field and you're trying to be as fast as you can and they're chasing you, you are constantly kicking that ball to keep it going. What Newton is saying is you don't have to keep kicking that ball. You give it one kick and it's just going to go and go and go and go at the same speed, unless there are other forces acting on it. And on Earth, on every soccer field that we play on, there's friction. Okay. So Newton's law, the addendum to Newton's law, which is pretty much the same thing, is only when friction is present or other forces are present, like air resistance, which is a form of friction, only when other forces are present is more force necessary to keep that thing moving. Otherwise, it will just keep on moving as it is in a straight line, constant speed, constant direction, and will just keep on going to the end of time. Or it'll just sit there to the end of time if it's just sitting there. Because stuff doesn't like to change. If it's moving, it wants to keep moving. If it's sitting there, it wants to keep sitting. That is inertia. Okay, so we will come to inertia and discuss what inertia is. Inertia is a fancy word for the property of matter that resists being moved or changed. So inertia scales with mass. A bigger object has more inertia. A sumo wrestler has more inertia than a newborn baby. A truck, a semi-truck, loaded up, has more inertia than an empty semi-truck because it's got more mass. A semi-truck full of, flour, bags of flour, has got a lot more mass and thus a lot more inertia than an empty semi-truck. So let's see. So imagine you're deep in space, okay? No gravity here. You're in deep space, far, far away from everything. You're in a space station and you get these mystery boxes and they're all the same. They're these sealed metal boxes and one of them has a bomb in it. But that the other, there's 5 boxes or whatever. The other 4 have other objects in it, but that one of them has a very heavy, very heavy plutonium bomb in it. How can you tell? I said heavy, I mean massive, very massive. All the other boxes are empty. You're in space, you can't weigh them. Well, how you would tell was by shaking them, assuming that doesn't set the bomb off. I don't know. Anyway, what you would do is shake them, because even if they have no weight, they're sitting on your hand, they're just floating. They're just floating in your hand, you can grab them, but there's no weight because you're out in deep space. But if you shake them, you will feel the inertia. You will feel it's harder to move it, it's harder to shake it than that empty box. And you can find out which of the mystery boxes has the bomb. Another example, let's see. My mom, this is more my life. When I was about 14 years old, my mom got obsessed with having us grind all of our own flour. So she would buy from like a farmer's co-op these really huge buckets just full of wheat berries, the unground up wheat. And then she cranked up a wheat grinding, old-fashioned 100-year-old wheat grinding mill. And me and my brother had to take turns turning that, and my other sisters, turning, and grinding the flour until we could make bread out of it. But it made it a lot harder to sweep the floor because you're in the kitchen and we've got all these big buckets, all these opaque, large buckets that my mom kept buying from this farmer's co-op. So you're sweeping the floor and there's various buckets in the way. And so to me, my 14-year-old self, I just kicked them out of the way while I was sweeping a section. So I would kick them all out of the way while sweeping a section, go to the next section, kick them back to the part I swept and sweep that part of the floor. Well, I remember I walked up to the buckets and I proceeded to try to kick it away while I was sweeping because my mom had just been to the farmer's co-op. And that bucket goes flying across the kitchen and smashes and bounces off the wall. I'm staring at it and I realized my mom just went to the farmer's co-op, so I thought the buckets were full. But it turned out that bucket was an empty bucket from like a month ago. And so I had kicked a mostly empty bucket across the kitchen when I only meant to scoot that bucket about 3 feet. The difference is that I subconsciously looked at that bucket and assumed it was a full bucket, that it was full of wheat kernels. And so I had calculated my kick to move that bucket about 3 feet on my kitchen floor with its friction as I was used to it. If I had been sweeping an ice rink, not that I'd be doing, but if I'd been sweeping an ice rink, I probably would have kicked it with less force because I would know there was less friction. But that was a linoleum floor, a good amount of friction there. This is what I mean when I say you are constantly doing physics calculations in your head. You are constantly looking at a surface, thinking about how much friction there is, thinking how much do I have to shove this, how much do I have to push this, how much force do I have to give it to move it in the direction that I want. If you play any kind of sports, you are constantly doing these sorts of calculations subconsciously, just sort of intuitively. People talk about, you get a feel for it. That's actually subconscious physics. That is what a feel for it is. Driving, when you're trying to turn across traffic, you're turning left and all that traffic is coming and it's not a protected arrow. I hate those. So you're looking, there's no protected arrow, and so you're having to decide, do I turn? Do I have enough space to turn? My sister was notorious for turning when she had barely enough space to make it. And my twin, my other sister, who's sitting in the passenger seat, used to pray, was always praying whenever my older sister was making a left turn because she was in the passenger seat exposed to the oncoming car, barely making it out in time. Anyway, that's an example of a physics calculation, and God is merciful, and my older sister did not mess up. If she had not calculated quite enough, she could have gotten a car accident. That's a lot of car accidents happen when people are turning left and they don't quite make that physics calculation correct. I had an example. It was very where I was sleep deprived and I was driving with my kids and I thought I had enough space to turn left and I did not. But thank God the oncoming traffic slammed their brakes on it enough, slowed down just enough that I was able to squeeze past. So that's an example of doing subconscious physics is very important, and err on the side of caution. Okay, so sorry, that was a little... Right, so back to my mom and the wheat in these buckets and sweeping the floor. So in my brain, I had thought that thing's a full bucket. That thing is very massive, or we would say heavy. That bucket is full of wheat. I need to kick it pretty hard to get it to move 3 feet so I can sweep this section of the kitchen. But it was not massive at all. It was empty. And so when I kicked it, that thing went flying far away. Because you intrinsically know that the more mass something has, the more inertia it has, the more it will resist change, the more it will resist movement. So you know that if you want to get this thing to move, you've got to give more force to push all that inertia, all that resisting, changing movement. So this is an example of something that's not moving, and we know it has a lot of inertia, and we're trying to get it to move. And so we have to give it a lot of force to push against all that inertia. An example of something that is moving, that has lots of inertia, that doesn't want to stop. So suppose you're sitting there, and you look up, and you see hurtling toward you is a pillow. You could duck, I mean that's your instinct, but you could probably just stand there, and the pillow will hit you in the face, maybe it'll sting a little bit. It will stop, stop as it hits you in the face and fall to the floor. Okay? Now imagine you're standing there, and you see another pillow hurtling toward you, only at the last second you realize it's not a pillow, it's shaped like a pillow, it's in a pillowcase, but someone just put a pillowcase on a bag of cement. How much fear do you feel as you realize that inside that pillowcase is a bag of cement hurtling toward your head? You should feel quite a lot of fear. Because in the case of the pillow, you knew that the pillow doesn't have a lot of mass. There's not a lot of stuff inside that pillow. It doesn't have that much inertia. Its inertia of moving will be stopped by your head without any damage to you. When you see that bag of cement in a pillowcase come hurtling towards your head, there's a lot of stuff in a bag of cement, or in fancy science talk, mass. There's a lot of mass in that bag of concrete with a pillowcase on it. And you know that your head is probably not enough to stop its inertia. It has a lot of mass, it has a lot of inertia. It will probably keep on going on its trajectory toward the floor with your head along with it, and you're gonna hit the floor until the earth stops the inertia of that bag of concrete and you're sandwiched in between. So on an intuitive level, we know that even though these things are the same shape and size, there's a pillow and a bag of concrete with a pillowcase, you know that that pillow, the pillow with the concrete has got way more inertia, and that the cost of stopping that inertia, when your head is paying the cost, you would much rather you have a less massive object like a fluffy pillow than a more massive object like a bag of concrete, because your neck, your head is paying the cost to stop that inertia. Here's another example of inertia. This is why they always say don't put little kids in the front seat of a car that has airbags that don't turn off. I think the modern cars, the airbags might turn off, but my more old-fashioned cars, the airbags do not turn off. And so I cannot put my little kids in the front in the passenger seat. Why is that? Because they made a airbag is supposed to help, in an accident, well, multiple levels of inertia. In an accident, you've got a car, and this is your car, and this is usually glass. So we'll make it a Jeep, just to make it easier so we don't have to think about, can I draw a Jeep? Okay, well, this is a Jeep. It's not a very good Jeep, okay? It's an open top Jeep, okay? And here you are, okay? Going 60 miles an hour, okay? And then all of a sudden, you hit, bam, into a wall. Let's make it a short wall. What happens? Well, you go flying out, right? Because everything in this, you feel the lurch as your body gets stopped, as all that inertia slams into this wall. And if you're not seatbelted, you go flying out and hit the ground. And that's actually what kills people in accidents. It's the stopping, when your body has to stop. All that energy, all that 100 miles per hour smash, you're down. Okay, so now this time you're wearing your seatbelt, okay? Your second life. Your first life, you died on the pavement. Your second life. This time you say, okay, I am wearing my seatbelt so that I am attached. I am secured to this Jeep. So if it hits in another concrete barrier, this time I am not going to fly out, hit the pavement, and die. So this time, same thing happens. You're trucking along, going 60 miles an hour, and you hit the barrier, and sure enough, your bum, attached by the seatbelt, stays nice and secure, but the front half of you wants to keep going. So what happens here? As you hit sudden stop, your head wants to keep going. You will lurch forward pretty dramatically because your bum, that's why they always want, you to have the seatbelt with the arms thing, but then people move, so then they have to make it sort of flexible, so they try to make ones that won't move, you jerk it, and they try various things with seatbelts, but this is what they're trying. Well, anyways, what happens when you're driving that car and you lurch forward, a lot of times people were smashing their heads into the windshield, the driving wheel, smash, and the concussion of that jerk from the top half of your body that wants to keep going, smashing into that was hurting people. And so they put in airbags. And what airbags do is airbags sense when you're crashing, and they will basically shoot out this giant, very fast-moving thing of air that will try to keep your head and the rest of your body back as it's trying to move. So it's kind of like a personalized, because if you think about the car as a whole room, if you imagine that you're floating happily in this box, or a fly, and then you smack it, you throw the box, a giant throws the box against the wall. Inside the box, you're going to keep on moving, and you're going to smack into the side. If that makes sense, similar to the car situation. You're going to smack into the side. So what are the contents of the box you're still going to hit? Because the contents, you and this box are all moving 100 miles an hour or whatever. You hit the wall, and the contents are going to try to keep going. You will see this if you get a clear bottle of water and fill it halfway up and you throw it, and if you can take a slow motion video, as it hits the wall, you'll see the water will try to keep moving. So if you're throwing like a plastic water bottle, it's not a very good picture, with water in it, and then you throw it against the wall, the inertia of the water, you will see the water will, for a brief second, will all slosh in this direction. So the water is still moving, even though the bottle stopped, and then it learns its lesson, it sloshes back and all that. So same here, you would hit this and then probably fall down. So your airbag is trying to push you back. Now the reason airbags can kill little kids and very small little old ladies is because what ends up happening is, instead of shoving them back like this, they're small, they don't have the mass. They're little, and so what ends up is they end up getting plastered by the airbag against the airbag has way more force than they need to push them back, and so it can like break their neck or whatnot. And that is why, it's because they're less massive than us. That's why they say, like, to ride in the front seat with a car with an old-fashioned airbag, you want to be like at least 100 pounds or something like that. Yes, what is your question?
So why are you showing a picture of a little kid getting killed by an airbag?
Jenny, only ask questions that have something to do with physics, okay?
Okay.
All right, so next to the, so we're talking about inertia. So the more mass you have, the more inertia you have. The reason little kids die with airbags is because they don't have enough mass, they don't have enough inertia, that it's like overkill. It's like this huge old airbag comes trying to fight that inertia that it assumes they have, and they haven't got it, and so they end up, it doesn't balance. It's like playing tug of war with a 3-year-old, and you're always gonna win, and they're gonna go flying off, dragged by the rope. Okay, so back to net forces. Okay, so talking a little bit about mass. So what is mass? Mass is the stuff. It's the stuff. So a lot of times we get confused and we think of stuff as weight. Now, weight is mathematically related to mass, but it's not the same thing. Why? If I go to space, my weight, if I go to deep space, my weight is 0. I don't weigh anything. That doesn't mean that I've suddenly lost my arms and my legs and my brain, you know, this physical body that I have. I still have it. It's still there. You know, the joke about the doctor tells the man to lose weight, and so he goes to Mars. Mars is less. So Mars' gravity field is weaker because Mars. So basically, the bigger the planet is that you're on, the heavier, the more you will feel it pulling on you. So the moon is a lot less massive than us, and so you go to the moon, and your weight, the amount that your weight is pulling on you is less. So if you're on the moon, you can do cool jumps. You can do cool like spinning ninja kick jumps. You can look like Jackie Chan or something. Okay. So on the moon, your weight is less. If you go to Jupiter, you're probably gonna be a little flatter. If you could even land, it's sort of a gas giant. But if you could kind of hover around somewhere, you're going to be so heavy. It's gonna be so hard to move your arms or anything. You're gonna just feel it because you'll be so much heavier. Not that your mass has changed, it's just that the more massive the planet is that you're on, the more it's pulling you down. So that is why we on Earth, when we're talking about things on Earth, we'll talk about weight like it's mass. When the doctor says lose weight, he really means lose mass, or specifically lose, fat. Usually they don't tell you to lose muscle. But anyway, so mass and weight are not the same thing. On Earth, as long as we're talking about, anything on the surface of the Earth, we can use them almost interchangeably because it's like a fixed mathematical connection between mass and weight. But as soon as people start going to Mars or whatever, I don't think they're going to talk about their weight in pounds anymore. They'll probably talk about their weight in kilograms, which brings us to kilograms are actually supposed to be measuring the amount of stuff, the amount of mass, the amount of atoms and whatnot that are there. Now, people get this mixed up all the time because they know that a kilogram weighs 2.2 pounds. And so then they decide that a kilogram is the same thing as weight. And then people talk about, oh, you'll weigh less kilograms on the moon, which they're kind of forgetting what a kilogram is supposed to be. A kilogram is supposed to measure the amount of stuff. But anyways, okay, mass is not volume. Again, remember, with the pillow example, a pillow full of fluffy fiber fill and a pillow full of concrete have the same volume, but one of them is a lot more massive than the other. Also, muscle, I've heard, I don't know, I haven't done the math, but I've heard that muscle is actually denser. There's more stuff, it's more massive than fat. And so, sometimes you'll see these like bodybuilder sorts and, if you look at their BMI, their body mass, BMI, whatever, the thing the doctors use. If you look at it, they're like, oh, you're obese. And then you look at the guy and he hasn't got a scrap of fat on his body. He's like all muscle because muscle is extremely dense. Anyways, mass. So mass is not weight. Mass is not volume. Mass is stuff. We're talking about stuff. Like if I go to space, my weight will drop to 0, but I still have all the same amount of stuff, of mass that I have on Earth as I will in space. Okay, now we're going to talk about net forces. So net forces. So let's start with tug of war. So assuming you've played tug of war, there's like usually a little flag in the middle, and usually you have a team on this side holding onto the rope. Okay, so we've got team B and team A. And let's see, a little team A. Okay, so we've got team B and team A. And usually their goal, say they've got a little line here in the dirt, their goal is to pull the flag. That's a really ugly flag. Their goal is to pull that little flag over their side. And if you've ever watched kids playing tug of war, or if you've played tug of war, but especially if you're watching it, you can sometimes see them turning red, just straining, pulling with all of their might. And slowly, slowly you see the flag inching that direction. This is net forces, because you think about the forces going on that little guy, or on that rope with the forces that are being exerted on it are much, much greater than that little tiny pull in this direction. But most of the massive force these guys are pulling on it is balanced by the massive force these guys are pulling on it. But these guys are pulling just a little bit harder, and so it's inching in this direction. Another way to think of it is you've got a little block here, and say someone is pushing with 100 newtons of pressure or 100 newtons of force in this direction. But his little sister comes and starts pushing with 50 newtons of pressure in this direction. When you finally see that block, it's going to be moving as if only one person was doing 50 newtons in this direction. Or here, maybe that's a little confusing. Or let's say she's doing 30 newtons. He's pushing 100 newtons. She's pushing 30 newtons this way. This is N for Newton, not north. And the net result would be as if one person was pushing 70 newtons this direction. Because you see some of those forces cancel, and whatever force isn't canceled out, that's the winner. That's the force, that's the net force. So in a situation with this block here, and let's say his other little sibling comes, and his other little sibling also pushes with 30 newtons, okay? So now the net force, we've got two little siblings pushing with 30 newtons on this side, he's pushing 100 newtons on this side. Now the net force is 40 newtons this way. Because you'll see that's 60, 100 minus 60, pushing this way. So the net force, and they often like drawing the net force as this cool little sigma F. The net force is when you add it up, or rather finish canceling everything out, what's left. The net force acting. Now, supposing these guys are evenly matched, and they've been pulling for 1 hour, and that little flag is just hanging out right where it was at the beginning. In this case, the net forces, the sum of all the forces from team B and team A, the net forces are 0, okay? Supposing these two little kids are pushing and the big brother's pushing 100 newtons, and then yet another sibling comes and pushes with another 30 newtons. Okay? So now the net force is, it's only 10 newtons because he's got 30, 30, 30. He's got 90 newtons. And then the baby comes and the baby just manages to push, or I should say the toddler. I'm going to draw another arrow, sorry. Okay, this one is 10 newtons worth. Okay, now the block isn't moving anymore. These 4 little siblings have managed to match their big brother in pushing this block. Now the net force on the block is 0. When the net forces are 0, when that flag is not moving, this is called equilibrium. When we say if something is in equilibrium, this flag is in equilibrium, this block is in equilibrium, that means the net forces are 0. The funny thing about this is you could literally have 4 kids pushing on this side, 1 kid pushing on this side, and the block being in equilibrium, or you could have everyone goes and eats breakfast, and it's just sitting there on the table, and its force is equilibrium. But either way, if the block is not moving, it's in equilibrium. So that's something to remember. If something's not moving, the force, all the net forces on it, net means you add up all the forces. Net force here would be this force with this force. Calculate them, how their vectors go. The net force on this block is 0. The net force on this is 0. So here we have, that is what equilibrium means. Now, if you put a book on a table, so I've got a table here, okay? And I put my book on the table and it's sitting there, that book, the net force on that book is 0. It's in equilibrium. It's not moving. Gravity is trying to. Gravity's pulling my book down. Is that on the video? Can you see if that's on the video? Am I going too far?
Yes, it's on the video.
Okay, great. Gravity, the force of gravity, so I'm going to do F with a little g for the force of gravity, is pulling that book down. However, the table is pushing that book up. So I'm going to do force, and sometimes people call this the support force. Sometimes people call it the normal force. It's the same thing. But it's usually, it's the reason. Now, supposing I come here and I put a giant chunk of, I don't know, titanium, I don't know, something super, super heavy on my table, and it starts to sink through the softwood of my table. In that case, gravity is winning. My table does not have enough support force. Okay, that's a little hard to imagine. Imagine this table is just a card table. You know those like little wimpy tables? It's a little, one of those pathetic little, I used to have one of these in college, pathetic little cardboard table with some plastic or something stapled over the top. And I can go and put my stack of textbooks on it. What happens? That table smashes. That table falls apart. It's a very, very pathetic table. And it falls. Why? Because the normal force, the support force of the table was not enough to match the gravity, the force of gravity of the stack of books.
What happens if gravity disappears? Do the books go up?
Gravity disappearing? Why would gravity disappear? So Jenny, suppose we're on a spaceship, okay? And we've got an artificial gravity field. And we've got our books sitting on our table. And then, I don't know, the average artificial gravity field thing blows up or whatever, is science fiction. What will happen to those books on the table? Well, it will still sit there. Why will they sit there? Because an object in motion will stay in motion.
But if an ant crawls under them, it's like
if a little ant crawls under them and slightly shoves them, then maybe that will be, well, depending how much inertia they have and whatever, it will slightly bump and can go drifting off the table. Now, the cool thing about normal force or support force is that it sort of balances, like it's pushing back. So for example, I can put a 10-pound weight on my table and it will just sit there. Now suppose I get the same table and I put a 100-pound weight on my table and it will just sit there. You might say, hey, in this case, the table is sending 100 pounds worth of support force, because remember gravity is doing 100 pounds. Sorry, this arrow is supposed to be here. I really need another color marker. And you might say, hey, then won't that same table send 100 pounds of support force and send this little ball flying up in the air because it's only 10 pounds? No, because it's sort of, the support force is kind of like a spring. Like the farther you pull it, the more it's pulling back on you. Like the support force will sort of just keep, it's supporting, it's a normal force. It's just pushing back. It's actually, like if I don't know if you can see my hands. I'm leaning my hands on the table here and then I'm lifting my feet off the floor. So the table is holding me up. What's actually pushing my hands back is actually the electrons in my hands resisting the electrons in the atoms of the table. It's like if you were a kid and you ever got those two, like the magnet trains that stick to each other and then you flip it around and you got like the back magnet and you're trying to force them together and they're pushing away each other. It's electrostatic forces. It's actually electrostatic forces that keep us from plunging through into the center of the earth because atoms are actually mostly empty space. Like they feel solid to us, but that pushback on my hand as I hit, oh, did I ruin the recording of this one?
No.
Okay, good. As I hit something that's actually electrostatic, and we will get into that in the second semester and it's very cool. But, sorry. Right. Okay, equilibrium. So it's fancy science talk, equilibrium. Forces are in equilibrium to mean that the net forces on something are 0. The net result is 0. These guys are pulling really hard. These guys are pulling really hard. It's just staying there. The net result is 0. This guy's 4 little siblings shoving on the block. He's shoving on the block. It's just going to stay right there. The net forces are 0 if it's in equilibrium. Okay. Now, how many minutes did we go? Jen, can you check the clock? I'm going to see if we will cover vector addition of forces.
What happens if the newborn baby starts pushing too?
Okay. Back to vector addition of forces. Oh,
34 minutes.
darn it. Okay, this is taking really long, and I forgot to talk. I want to talk a little bit. Okay, I'll finish about vector, and then I'll talk a little bit more about inertia, because there were some examples that you could use. So vector addition of forces, we'll cover that next week. I'm just going to go back. And tension forces, we'll cover that next week. I'm going to talk a little bit about applications for inertia. Okay, so on page 47 of your textbook, if you open it up, there is an image of a strong man trying to stop a truck. And he's very strong, and he stands there and holds his hands out, and the truck keeps going, and he's like stuck on the truck. It does not matter. We know in our soul, it doesn't matter how strong you are not going to stop a semi-truck. That's why Superman never made any sense to me. But anyways, it's because like you see this massive object coming, one little person, he's not going to be able to balance. He's just going to end up plastered to it, and the whole thing is going to keep moving. This is why in those sort of kind of Asian anime style, almost surreal fight scenes, when you see a hero fighting some giant beast, and like the hero punches the beast's head and the beast kind of recoils, it doesn't make any sense. Because if you look at our hero, if the beast's head is like 5 times the size of the hero could body slam himself into that beast. Like how much, I mean, I guess unless he's going like supersonic speeds or something. We'll get to that later with force equals mass times acceleration. But what I'm saying is that from whatever speed that you can actually punch, that you can actually hit, like you just haven't got the mass to move that giant monster's head. Like you can play, it's like the strongman trying to stop the semi-truck. The semi-truck is so much more massive. Like it, as hard as a human being can punch, you're not going to be able to do much with that beast's head. What makes a lot more sense is make the monster's inertia work against him. Note that if you're going to punch him, he's barely going to move, right? Because he's got all that inertia. He's so much more massive than you. So in this case, if you skewer him, well, you don't have to hold him in place while you skewer him. It's not like trying to skewer a marshmallow that keeps floating away and you gotta hold it. Because in this case, the monster's head is just gonna stay there. If you try to skewer him, poke a hole in him, shoot him with an arrow like Bard shooting Smog, it will pierce one little spot. Like that's more plausible. But trying to punch a monster, like good luck. Like that thing is so massive. Even if you turn your entire body into a fist, you're not gonna get very far. Space combat applications. In deep space, so we're away from gravity, but we still have to deal with inertia because matter is still matter. It still has that massive amount. So the smaller ships in a space battle will be able to maneuver much faster than a big ship. They can zip around that big ship. Now, if the big ship gets to them, they're toast. Here's an example of the Battle of Thermopylae. I think that was when the Athenians were fighting. I may have gotten the name of the battle wrong. My son's not here to straighten me out. But anyways, the Athenians are fighting the Persians in the Bay of Athens. And I think Athens was on fire at that point. No, not Thermopylae. Excuse me. Wrong battle. Salamis. This is the Battle of Salamis. Thermopylae was the Spartans, I think. Right? 300 Spartans and all that. Anyway, this is the Battle of Salamis. And they were fighting on the sea. And the Persians had these huge ships. And if a battering ram on the end of a giant, massive ship with all that inertia, you are dead. A little ship with a little pokey, ram ramming you, it's only hitting you with all the inertia of that one ship. It might hurt you. It might, or, might not. It's like the equivalent of, well, anyway, sorry. So you've got this little ships and big ships. But in the Battle of Salamis, what happened is that the Athenians were able to, sorry about that. The Athenians were zipping around and were able to punch lots of little holes in the Persian ships because they could move much faster. Why? Think about how many rowers, how many men are having to row to maneuver that little ship. Now you've got this giant, massive ship, so much more mass, so much more inertia. Think how many rowers they had to row to try to move their ship. So the Athenians were able to be faster. They had less inertia. They were able to zip around and punch holes in the Persian ships. But I think Athens was already on fire at that point. It was a very exciting battle. Anyways, so another example. So in space combat, likewise, your little guys will be able to zip around much faster. If the big guy makes contact with your little guy, then your little guy's toast. But your little guy's best shot is to zip around much faster. If you've read the book Prince Caspian, it's kind of a similar idea when you've got Miraz fighting Peter. Peter was small and fast, but he wasn't as strong as Miraz. His best hope was zipping around Miraz and getting Miraz to, exhaust himself trying to fight him. But if Miraz actually landed a hit on Peter, Peter was done. But think about that inertia, all that inertia can be a plus, like a battering ram. The more massive, the more inertia your battering ram has, the more destruction it's going to do to the door. But it can also be a negative if you can't slow yourself down as fast. Okay, example is a lot of places that have mountains, so not Phoenix, but a lot of places have mountains. So next time if you're ever driving through Colorado or somewhere like that, you will see what people call runaway truck ramps. And actually in Colorado, I think there's one every single mile from the stretch that we went through the Rocky Mountains. Because what happens is that you've got this massive loaded semi-truck with all this inertia, and he's trying to maneuver up and down these mountains, and sometimes inexperienced drivers will use their brakes too many times, and then the brakes overheat and fail. And then that semi doesn't have brakes, and it starts going down, 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 faster and faster and faster and faster, and then you're toast. You veer off the mountain and die. And I know about this because my family decided to do a vacation in Colorado when I was 20. Yeah, no, 20. Anyways, decided to do this vacation in Colorado, and my teenage sister was driving the car. It was a Suburban, and we decided to bring the pop-up trailer with us. So we've got a Suburban with a pop-up trailer lugging behind. And at some point, something funky happened to the car and the brakes failed. And we're going faster and faster, and you could feel it when the brakes failed, because there's a slight downhill, but you could feel it going faster and faster and faster. I mean, she got her foot off the gas, and it was just going faster and faster and faster. And as we're going down that mountain, and we knew very soon we'd be doing like 100 miles an hour and just like veer off the road. There was like no way. We were praying, and my dad, who was in the passenger seat, says to her, "Runaway truck ramp," and we see it coming up, and we know we've got one shot at it because she can't slow down at all, and she has to pray that no one's in the way when she's trying to get to the runaway truck ramp. Hardest I ever prayed in my life. And we veered into that runaway truck ramp, and it was basically this steep, so the runaway truck ramp is basically this steep curve up a mountain. So you've got your road, everyone's going downhill, and it's the side, so kind of like an exit ramp, but it goes up. So we're going through a mountain here, and there's the runaway truck ramp, and so she steers up, and we go up, 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 up. So what is the runaway truck ramp doing? It's taking all that energy all that inertia, so it's taking all that inertia that your semi-truck, your loaded semi, or in this case, the pop-up trailer in the back of our Suburban, it has all that inertia, it doesn't want to stop. So these very steep runaway truck ramps full of gravel, what it's doing is it's taking the gravitational potential energy and it's balancing it against to eat up all that inertia. It's like throwing that ball in the air and the gravity works against it and it comes down. So it's basically, they try to make these runaway truck ramps so steep. It was so steep, I was afraid we were going to roll down when we finally stopped. It's incredibly steep, but what it's doing is it's eating up the energy of all that inertia of that massive truck to save us, so that we don't go flying off the mountain. And I remember being worried at one point that we were just going to keep going, because there is a top to the runaway truck ramp. I was afraid we were just going to go down the mountain, but thankfully we did not. We stopped. Okay. So gravitational attraction. So I was going to say gravitational attraction also, well, we'll talk about that next week. I'll talk about that next week. So I think that's enough for now. I'm sorry it was a little rambly. I will get better at this. See you all next week.
Can I get in the video?
Oh, Jenny wants to be in the video. Hi, there's my assistant.
Hi, this is me.